This is a video for MEI Core Pure Mathematics, first order differential equations, 1.6, finding integrating factors. If we have differential equation of the form dy by dx plus py equals q, where p and q are both functions of x, we can solve this, provided we can turn the left-hand side into a perfect derivative. If it's already a perfect derivative, then we can solve it straight away. If it's not, we need to multiply it by some function of x, and we call this function of x an integrating factor. In a previous video, we were given the integrating factor to use, and we found that that then became a perfect derivative and we could solve it directly by integration. So what do we need to do? Well, we want something, a function of x, which when we multiply through, we get our function of x dy by dx plus our function of x times p, which is also a function of x, y, is equal to obviously our function of x times q, which is another function of x. And we want it so that this thing here is a perfect derivative. Now it turns out that we can show that fx has to be equal to e to the integral p dx. And this integrating factor can be used in all situations involving this kind of differential equation. So what we'd get is e to the integral p dx dy by dx plus p e to the integral p dx y is equal to e to the integral p dx q. And if you just look at this for a second, you'll see that if I differentiate e to the integral p dx, I'm going to get e to the integral p dx again, but multiplied by the derivative of the power, which is p. So this thing now is a perfect derivative, and in fact it's just the derivative of e to the integral p dx y. And that's therefore equal to, on this side, e to the integral p dx q. That's just confirming what we've said. We want something that turns the left-hand side into a perfect derivative, and that something turns out to be e to the integral p dx. If you want a more complete proof of that, well, that's beyond the scope of this video, and I think you could usefully look at your textbook for that. Okay, let's have a look at this. If I think of this function 1 over x as being the p and this function over here as being the q, then my integrating factor is e to the integral p dx, which is e to the integral 1 over x dx, which is e to the log x. I don't need to have a constant of integration here, and indeed if I did have one, it would just throw a constant in at the end, and that would multiply right the way through and would cancel out. So that is just going to be x. So my integrating factor is x, and in fact this is the integrating factor we were given for this equation in a previous video, but let's work it through anyway. So I've got x dy by dx plus y is equal to 4x cubed. Left hand side I know is now a perfect derivative, so that's d by dx of xy. In the early stages you might just want to double check that that is the case. I'll get x dy by dx plus 1 times y. That's equal to 4x cubed. And so now integrating both sides, I'm going to get xy is equal to 4x to the 4 over 4 plus c. And so dividing through by x, my general solution is y is equal to x cubed plus c over x. Again, there's that worked through neatly for you so you can see what's happening. There we come down to our perfect derivative, having used this integrating factor x, and there's my final solution at the bottom there. Okay, let's have a look at this example then. Well, the first thing to note is I haven't got dy by dx on its own. So the first thing I'm going to need to do is to divide through by cos x. So this is going to give me dy by dx plus 2 tan x y. I'm going to keep the brackets so that we realize that 2 tan x is a function on its own, is equal to cos squared x. Now my integrating factor is going to be e to the integral p dx, remembering that this bit is p and this bit is q. So that's going to be e to the integral 2 tan x dx, and that gives me e times 2 log sec x. Well, that's e to the log sec squared x, and that's just going to give me sec squared x. So if I multiply through by my integrating factor sec squared x, I'm going to get sec squared x dy by dx plus 2 sec squared x tan x y is equal to sec squared x cos squared x. Well, the left hand side is a perfect derivative now. It's d by dx of my integrating factor times y, and that's equal to sec squared is 1 over cos squared, so this is just 1. Integrating both sides, I'm going to get sec squared x times y is equal to x plus c, and rearranging, I'm going to get x plus c times cos squared x. There's the first bit of that worked through to establish the integrating factor is sec squared, and then starting from the integrating factor multiplying through, I end up with that result. And there you'll see again the bracket's been put in front so that we don't have anything ambiguous about the scope of the cos function. So in summary then, if we've got a differential equation in this form, where p and q are functions of x only, e to the integral p dx is the required integrating factor to make the left-hand side perfect, And if we multiply through by that, we can then just integrate both sides. So I've got the integrating factor times y is equal to the integral of the integrating factor times q. And that should all then just work out. And this will work for all first order linear differential equations that match this format. That was the final video in this sequence for first order differential equations.